So today I'm going to continue talking about conditional language modeling, but we're going to introduce a really important concept in neural network models called attention, which solves a lot of the learning problems that we dealt with, or that we see appearing in the conditional language models that we talked about on Tuesday. And this attention-based models are used in sort of state-of-the-art systems for a tremendous number of applications these days. Okay, so to review what I mean by conditional language models, we're building a sequence model over words, and we're conditioning on some representation of another input. So we're going to use the chain rule to decompose this. We saw, so basically if we're doing a translation like a application like machine translation, we get some input and we want to use, say, an RNN to spell out the translation of this. And Ilya Sutskever and colleagues proposed a very simple model where they're going to read from right to left the input sequence using an LSTM and then feed that in as the starting state for an LSTM that's going to decode. And if you train this really well, you can get pretty good translations. And so today I've got kind of Oxford-themed examples. The problem with this model is that we're compressing a lot of information into a finite-sized vector. And if you think about sentences, well, obviously we can't talk forever, but there's really no upper bound on the length of sentences that we might deal with. You can always add to the beginning of a sentence, John said, and you've still got a valid grammatical sentence. And putting more and more information into a fixed size thing should be somewhat troubling. And a couple years ago, a sort of well-known semanticist or computational semanticist called Ray Mooney sort of vehemently declared that you couldn't put the meaning of an entire sentence into a vector, and he added some a little bit of color to that sentence. So I think the field took notice of this complaint, and so today's lecture is going to be in part solving this objection. The second problem that we've got is that gradients in that model that we just looked at, they've got a really long way to go. And LSTMs are great at avoiding some of the worst of the vanishing gradient problems that RNNs, simple RNNs have. But even LSTMs forget. So we maybe should be worried that we're making the learning problem too difficult. Okay, so these are really the two big problems. So what are we going to do? We're going to talk about using attention to solve both of these problems in one. So we're going to look at two applications to motivate the solution. We'll start off with machine translation with attention, which is historically, that was where it was first developed. And then we'll talk about how it was applied to image caption generation. All right. So let's think about what this vector problem means. Well, basically, vectors are fixed size, so what we're going to do is we're going to start representing the source sentence as a matrix rather than a vector. And this matrix is going to be variable. It's going to have a variable number of columns. So longer sentences are basically going to get more capacity to represent the sentence than shorter sentence. So we've got to figure out first, how are we going to represent a sentence as a vector, as a matrix? And second, we're going to have to figure out how to condition on this matrix when we generate the target sentence. And since obviously these matrices are variable in size and neural networks tend to like things being all of one size, we've got to come up with a solution there. And this, the mechanism that we come up with here is going to solve, obviously the capacity problem, but at the same time it's going to solve the gradient flow problem. Okay, so the basic idea is we want to have a fixed number of rows in this matrix that we're going to use to represent sentences, but we're going to let the number of columns depend on the words. And in fact, usually we're going to say that, so here, this F, this is going to be the sequence of words we're conditioning on in the translation task. I'll write F because it stands for, it's used conventionally in MT papers to indicate the foreign language that you're translating from. And what we're actually going to say usually is that the number of columns in F is just going to be exactly the same as the number of words. So each word gets its own column. But that's not necessarily a requirement. So we'll have things like, here I speak some German, so my examples are often from German. I'd like a beer, take care, or this great quote from Nietzsche. And we'll just have matrices of different sizes here. So how do we build these matrices? So I'll review a couple of different strategies for representing a sentence as a matrix, including the ones that are widely used and also maybe some ones that should be explored a little bit more. So the simplest strategy we might use to represent a sentence as a matrix is to say, well, we know how to represent words as vectors. We've spent a lot of this class talking about learning word embeddings. But we can simply then take all of the vectors from for each of the words in the sentence and concatenate them into a matrix. So we just stack these vectors next to each other. This is the simplest possible model. In fact, it's so simple nobody really bothers to publish how well this works. They don't use this as a baseline. But I think in some cases, when you are designing models for new problems, you should always think this maybe will work well enough. So here the idea is we've got embeddings for each of these word types, these 4 vectors, and they just feed into this matrix like this, where the ith column of F is the ith word vector. So we then have a matrix that is n by length F to represent this sentence. A common strategy for working with matrices of variable sizes in neural networks is to use convolutional networks. And so we can think about saying, well, maybe we want to let these words interact with each other and extract higher level features from this matrix that we've built, sort of like we want to take an image and extract higher level features in image processing. So we can put a few layers of convolutions on top of this. This was actually proposed somewhat later. In fact, it was only really explored in a submission to iClear that just went in this fall from Facebook. And it's, of course, closely related to the neural translation model that we talked about on Tuesday by Kalkbrenner and Blunsum. The only difference is rather than eventually ending up with a single vector representation, we're going to have a matrix up at the top. We're going to cut off that last component. And so, yeah, this last line says, convnets, when we work with them, we usually do use them to compress down to a single fixed size vector representation. For sentences or for applications where we want a matrix in the end, we're going to leave this out. Okay, so schematically, this will look something like this. We'll concatenate our vectors together just like we did in the previous model, and now we'll run some convolutions on top of it. So we'll have some filters, we'll do our standard convolutional operations on it, aggregate them together in some way, and we'll be left with a new vector, a new matrix representing this sentence. And so here, the number of columns is going to be some kind of function of the length of the input sentence. So convolutions sometimes add or remove columns from matrices due to how they're implemented. So we might expect there to be some variation there. So these two are things you ought to think about whenever you're considering building matrices. These are great neural network tricks for building matrices. But for machine translation, the most widely used strategy is to use a bidirectional RNN to build this matrix. So the idea here is that we're going to have one column per word, just like we did with this simple concatenation operation. But what each column is going to consist of is going to be 2 halves, 2 vectors concatenated together. It's going to be a forward representation of the word. So we're going to use an RNN to read the input sentence from left to right. And we're going to take each hidden state and call that its forward representation. we're going to take a second RNN, and we're going to read from right to left. And we're going to take, at each time step, that hidden representation and call it its reverse representation. And so if you concatenate all of these together, in some sense you have a representation of the word in its complete context. You can see everything to the left in the first half of the column, and you can see everything to the right in the second half of the column. So in principle, you've got all the context you could possibly need at every position. Typically, we don't run simple RNNs. We use these gated things like LSTMs or GRUs to read the LSTMs, but the idea is simple. And this is an appealing representation because we can deal with sentences of arbitrary length, and if there really is an important word that's going to influence how you interpret a word, say at the very end of the sentence, and these things are far apart, the model could, in principle, learn this. Whether it does is obviously an empirical question. So schematically, this looks like this. Here's our sentence again. We're going to run the forward RNN in this way. At each time step, we're going to have this H1, 2, 3, and 4. We'll do the same thing running in the reverse direction. You can stack these things and make them deep. Depth seems to help a little bit. Obviously, the number of parameters grows, and it can get difficult to propagate errors through very deep architectures. But if you've got enough data and good optimizers, that can be helpful. But schematically, this is the basic idea. And then what we're going to do is we're going to concatenate at every time step those two hidden states together and build a matrix like this. So we'll have here a matrix who has 2n rows and one column for every word. Is this clear? Yeah.
We don't understand like those basic vectors. I mean, how do you choose a dimension, or like what is the reference? Is this like the whole vocabulary?
Right. So these are word that x1, 2, 3, and 4. Those I'm assuming are word embeddings. So each of those will be represented by a projection into some low-dimensional space. The number of dimensions that we choose for the word embedding is going to be a matter of you're going to have to experiment to figure out what works. In practice, 500, 1,000, 2,000 dimensions are plenty for most of these problems. That's going to interact, though, with the amount of training data you've got. If you use very large vectors and you don't have very much training data, you're going to tend to overfit. If you don't use enough dimensions, you're not going to learn the function well enough. That's right. That's right. Yeah, one thing I'll mention here is we don't do a lot of pre-training, so we don't often run word2vec and take the word embeddings that are used and then feed those in as our initial vectors for x1, 2, and 3. It doesn't seem to help in very many cases. Basically, what word2vec learns seems to not give you very good representations for this task. On the other hand, machine translation, as I mentioned last time, is a great task because there's so much data out there. So if we were working on very low resource machine translation, pre-training is probably more effective. Most of the work at using neural nets that's been going on for the last 3 or 4 years since this was really proposed has focused on much larger problems where we really have enough data to learn all of those parameters just as starting from an initial random point. But yes, there is a projection matrix for the vocabulary. So we'll start with a one-hot encoding of each word. We will right multiply the projection matrix by each of those vectors, and that'll give us the x1, 2, and 3. All right, so where are we in terms of representing sentences as matrices in 2017? There are a lot of ways to construct F. There's very little systematic work comparing them. There occasionally people will propose a new technique and they will compare to maybe one other thing, but we don't really know what's going to work, and this is going to be explored as people try and build better and better systems, I suppose, in the coming years. There probably are many more undiscovered things out there. So convolutions have only recently started coming back in the context of machine translation. I think there are a lot of interesting applications there. Convolutions are kind of nice because they let you learn local n-gram relationships that are we know to be really, really important in language. And if you're going to translate something, then that seems like something you want to be able to capture. There's also been some recent work looking at including linguistic information in the form of part of speech tags and syntactic parses when representing the sentence as a matrix. So rather than just embedding a single word token, you'll embed the word together with some information about the syntactic role that that word has in a particular sentence. So you'll sort of say, it's not only a Kiko, it's a Kiko plus the fact that she's the noun subject of the sentence. And you can imagine that that's useful information. And maybe the model will learn it, but you can also supervise this stuff. Another thing to keep in mind that we tend to forget in NLP in general is language consists of multi-word expressions, things like pain in the neck. We probably don't want to treat each of those words independently. Yes, LSTMs and neural networks can learn things like this very effectively, but again, if you have prior knowledge that says this is a unit and it doesn't have any compositional meaning, we might be able to get some increased data efficiency by conditioning on that fact or building representations of units that are actually larger than single words, and this so far has been underexplored. So I actually think this is coming up with better, more intelligent architectures that build in more knowledge about language and how it works is something that could be done to really improve the performance of MT systems. All right, so let's now go on. Now we've figured out we can represent sentences as matrices. We don't know maybe which one is the best. That will be an experiment we can run. But we now need a way to go from a matrix to a sentence. So Dmitry Badenow, in a paper that was actually only published in 2015, although it appeared 6 months earlier on Archive in 2014, they proposed he and his colleagues proposed using what they called attention to translate from matrix encoded sentences. And so the high-level idea is really pretty simple. So we're still going to be using an RNN to generate words one at a time in the output language. And at every time step t, the RNN is now going to receive 2 inputs. So in addition to its recurrent inputs, so the ht minus 1, ct minus 1, things like that. So it's obviously going to receive an embedding of the word that was just generated. That's how it knows to continue to pay attention to what it's predicting at test time. The second thing is going to be a fixed size vector embedding of a view of the input matrix. And the idea is, as time progresses, we'll be paying different parts of attention to that matrix and pulling out a fixed size vector encoding of the information we need at that particular time step. So how do we get a fixed size vector from a matrix that changes over time? So they actually propose a really simple idea. At every time step, there's an attention weight mask called AT. So A is a vector whose length is the number of columns in the matrix. So in a model where the matrix has a number of columns equal to the length of the source sentence in words, you just have a weight for every word in the input sentence. And the weights are between 0 and 1, and they sum to 1. So it looks a little bit like the parameters of a multinomial or categorical probability distribution. And what we're going to do is we're just going to multiply that matrix F by that vector AT at every time step. And what that's going to give us is a weighting of those columns, and we'll call that the context vector at time t. And so the weighting of the input columns at each time step AT is called attention. Okay, so how does this work schematically? So here's our basic unconditional RNN. We feed in a start symbol. we sample we get a prediction, we sample a word, we feed the representation of the word in at the next time step, and we keep doing this until we get to the stop symbol. So now, when we're working with attention, what we're going to be doing is we're going to, again, start with a start symbol. But in addition, we're going to have this matrix off to the side, which is going to encode our sentence that we want to condition on. And what we're going to do is we're going to use the previous time step of the RNN, and we're going to use that to construct this attention weight vector at each time step. And we have to use the hidden state at the previous time step because we haven't yet computed the hidden state for the new time step, because this is going to be an input that's used to generate h of t. So we have to use h of t minus 1. So what we're going to do, and we'll talk about the details in a second, is we're roughly going to go through and we're going to compute some function that compares that hidden state with the columns of the matrix. And this is going to give us an attention weighting. And so I've drawn that here where sort of darker colors indicate maybe a higher attention weight. And that's going to be a sub 1, so the attention at time 1. And you can see, this isn't a real model. I made this up, but here we're attending mostly to the leftmost word here, to ich, which means I, which is probably a good word if you start translating the sentence, which means I would like a beer. It translates roughly in that order. We probably want to start attending. So if we have a good attention model, this is probably a reasonable thing to do. So we then take the matrix vector product, we get the weighting of those columns, add them together, and that gives us this context vector C1. So it's just this. And then that feeds in parallel to the embedding of the start symbol at time 1. Then we run the RNN as usual. We compute a hidden state. We sample a word from the vocabulary using that hidden state representation. And then we now go to the second time step. So here, again, we're going to feed in the word that we just sampled, I'd, or at training time, we're just going to use the word that we observed in our parallel training data. And we're now going to recompute the attention. Only now, instead of using h sub 0, sort of an initial state to build that attention vector, we're going to use h of 1 to compute the attention vector. So now you'll start to see how the attention vectors can evolve over time, because they're going to always be looking at a new hidden unit at every time step. So now we'll get something maybe that looks like this. So maybe we're going to be attending to column 2 a little bit more strongly, which is, again, good for this task. And then we'll sample, we'll feed that in, the matrix vector product there, and we'll get the translation like. And then we keep doing this as usual until we end up with the stop symbol. And then our translation is done, and we can go home. So I want you to notice another thing here. If you keep track of the attention weights over time, you can kind of look at them, and you have a history of what the model was paying attention to while it was producing a particular output. This is actually really useful if you look at a model that's produced some crazy output, and it's translating out of a vector, you really have a lot of trouble figuring out what it was thinking. Neural networks in general are hard to know what they're thinking, but attention is a very interpretable component. So you can see we've kind of got this diagonal here that says, first we translated the first word and then the second word and so on. Yeah.
So we have like a variable dimension vector, a fixed size matrix, and like how is this vector just like fixed resize vector the RNN? Explain that.
Sorry, I didn't understand the question.
The attention vector kind of like it grows.
So the attention vector at every time step is going to be, it's going to have, the number of components is going to be the number of columns in the, it's going to be the number of columns in that matrix, so the number of the words in the sentence. So for a fixed sentence at every time step, the attention vector is the same. But if you keep track over time for every word you generated in the output, you can just write them down. We don't actually do anything with that matrix that I've drawn there in the lower left-hand corner, in the lower right-hand corner. That's just something you can use to introspect the model a little bit.
And then we just use that to weight the column of the matrix.
Right. So basically, at every time step, what we've got here, we're attending to the last column. That's what the dark circle up there means. And we're going to multiply this matrix by that vector. And so effectively what that's going to do is take most of that column there and pass, the product is going to compute something that basically you can think about the matrix vector product as taking every component of this vector here, multiplying by the column, and then adding the resulting vector together. Is that clear? So it's a weighted combination of the columns.
Great.
Yeah.
How do the attention vectors update? How does it go from A1 to A2 to A3?
So we'll talk about exactly how that works in just 1 second. But it's at every time step. The crucial thing is when we're computing the attention vector at time 2. So we've already done A1 here. Now we want to compute A2. And so what we're going to do is we're going to look at the hidden state, which I've just drawn as this opaque circle up there. And we're going to construct A2 by comparing that hidden state to this matrix down there. And it's going to basically be, that model, which we're about to talk about, is in charge of finding how much weight to give to each column. Okay, yeah?
This model predict null words, because it seems like it's predicting just as many words that they were in the original sentence.
Oh, no, it can, yes. So in this case, yeah, I should have probably made that a different length. It can. So there's no constraint that says you can that you have to attend to a word only once, or at least once, or anything like that. In fact, there's no supervision on the attention at all. This is just something that the model has to, that we make available to the model so that it can figure things out. It doesn't have to use it the way we've attended. So. But basically, you can generate words. So you might translate this sentence as, I would like a beer, for example. And in that case, you might expect the attention to do something like, at time 1, you would attend. So this little German lesson, the second word in the German sentence, that is a inflected verb that means would and like together. So we might attend to that word twice in translation. And the RNN language model can just keep spitting out words as long as it wants. In this case, they're the same length, but in practice, sentences are a very different length. And this is actually a really important aspect of the model. We don't make any assumptions about the order that we're going to progress through that matrix, which columns we're going to attend to in which order. We also don't require that the sentence has any particular length. We don't have to, for example, decide how many words we're going to generate in advance. And we certainly don't have to have them have the same number. Yeah?
Can you give a bit more color on how the mask is generated? Is it like assumed to be normally normal, or is it sums up to 1, but is there any other descriptions?
Just that it sums up to 1 and everything is greater than or equal to 0. And that is exactly the topic of the next couple of slides. So how do we compute A sub t? So I'll go in detail through a couple of models for doing this. It's actually a really, really simple model. And this is a variant of this attention mechanism is used in almost every attention-based model. So basically the idea is you're going to take h of t minus 1, that's the current RNN state, and you're going to use that to query the columns of the input that you want to be able to attend to. And a good mechanism for querying anything is an inner product. So if you have 2 vectors, and you can think about the columns of that matrix as vectors, and if you've got another vector, say the hidden state, you can get a kind of similarity metric by taking the inner product between each of these things. And so we make this a little bit more flexible by not saying, well, we don't want to query the h of t directly. H of t is probably encoding a lot of extra information, so we want to do some transformation of h of t, which I'm calling the hidden states of the output network here, S of t. That's what Badenow used in the paper. And we called the h of t's in the input encoders h, so I wanted to pick a different name here. So this S of t, think just hidden state of the output RNN. And so what we're going to do is we're going to project that here just with a linear map onto what we might call the expected input embedding, or the query embedding at time t. And then what we're going to do is we're going to take that RT and we're going to take an inner product with every column of the matrix. And the inner product of two vectors, of course, just a scalar. And so we're going to get a scalar for each column of the input matrix at each time t. And so if we've got a list of scalars for all the input words, we're going to then exponentiate and renormalize that to get this property that they should be greater than 0 and sum to 1. So we can do this a little bit more efficiently than looping over things and taking selecting a column and taking an inner product. If you want, you can think about matrix vector multiplication as just repeated inner products with every column every row of the matrix. So what we do is you can write that, we can get these unnormalized attention weights, which I call UT here. It's called ET in the paper. I try and give the notation, but I like to have a consistent notation between all the slides. We take this transpose of the F matrix and then multiply that by this R vector, this query vector. And that's going to compute a vector who has the number of, its number of rows then, because we've transposed it, is going to be the number of words in the sentence, so the number of columns in the original untransposed F. And then we're going to renormalize that vector, exponentiate and renormalize that vector. So UT is now going to have the number of rows equal to the length of the sentence. So we now exponentiate and renormalize to get our A of t. So is it clear what this, what this is doing, and what the dimensions are? Okay. Okay, and then finally, we're going to take that AT vector and we're going to multiply it by F. And the dimensions again work out because we've got the right number of rows in that vector. Okay. All right. So that's a really simple model. In fact, that's so simple they didn't even use it in the paper. There's a slightly fancier model. So this assumes a linear interaction between the hidden states and the columns of F. It actually does work pretty well in practice. A lot of people have simplified to this, but since Badenow used this second model and this work has been terribly influential, I want to show the real thing. They just changed the definition of UT a little bit. So instead, what they're going to do is they're going to multiply that matrix F by a learned weight matrix W. And that's just going to be, say, an n by n matrix, where n is the number of dimensions of your input representation columns. And then we're going to add, so matrix, we're going to have this matrix, and we're going to add to it this query vector. And of course, when you add a matrix to a vector, that's not really defined. So what we want is plus to broadcast over all of the columns in WF. We're then going to pass that transformed, that resulting matrix through hyperbolic tangent, and then take and then multiply that by a vector VT. And that's going to give us the new unnormalized weights. So basically what this is doing is computing a representation of, it's using a linear similarity, nonlinear similarity function rather than this inner product-based representation. So you can learn slightly more complicated interactions. Yeah?
UT was the attention weight, right?
UT is the unnormalized attention weights.
Unnormalized.
Yes. So then we're going to still pass that through. So then if we go back to the previous slide, down at the bottom, we still have to do the softmax, we still do this multiplication by f and all of that. So it's just different definition of UT.
So this is 10H never gives us like negative attention or something.
Right. So you do, if you take out the softmax, you could still optimize this. It doesn't work nearly as well. So that definitely is valuable.
I'm not looking at this.
Okay. Okay, so we can put this all together, and this is neural machine translation. This is pretty close to, if you go to Google Translate, at least in the languages where the new neural system has launched, this is pretty close to the system that's run. I mean, it runs on probably thousands of computers and things like that. I don't actually know very many details about how it's deployed, but it's basically this model. They wrote a paper on it, so this is all public knowledge. But you start out, you encode your input sentence f as a matrix, and then you initialize with E naught being the start of sentence symbol. We're going to start with S naught. We have to define what's the input representation going to be of that decoder RNN. So that, normally we compute these things recursively, but we need a base case to go back in our induction and start with. BadNow uses a linear transform of the left reading sentence's final state. Actually, if you think about this for a second, this is exactly what the initial state of the Syskever sequence-to-sequence model was. So they kind of wanted to start, at least have that model as a special case of this. If your sort of attention weights were always 0, which they can't be because they don't sum to 1, if they did, you would reduce to the Syskever model. But you could also learn this. And then you have this while loop where you keep sampling subsequent words, or maxing, whatever you want to do, until you sample an end of sentence word. And during training, what you're going to do is, rather than sampling, you're going to use the empirical E sub t word that you see in your training data. And so then what we're going to do is we're going to compute this expected query, this expected embedding that we're going to use to query f with. That's R of t. We're then going to compute the unnormalized attention weights using either the BadNow model or the inner product model. We're going to softmax to compute the attention weights that are greater than or equal to 0 and sum to 1. We're going to then compute this context vector CT. Then we're going to feed in to the RNN using the standard RNN dynamics. We'll feed in the previous hidden state, S sub t minus 1, and a concatenation of an embedding of the previous E sub t and the current context vector that we've just computed. And then we have a new hidden state. We'll project that out onto the space of the vocabulary and take a softmax and have it be able to compute a probability of every word in the vocabulary. And so here I've drawn that as we're just going to sample we're going to sample E sub t from the categorical distribution in that way. And so at training time, that'll convert to take the negative log probability if you want to minimize cross entropy. At test time, it could be sampling or argmax or whatever it is. This is sort of a generic way of writing both the training and testing code here. So, is this clear? Everyone with me? Okay. It's easy, right? It's 10 lines of, well, some language. Okay, oh yeah, here's another thing. When you're implementing these things, we want to save as much computation as possible. So, it's useful to think, what can we factor out of models like this? We notice we're doing W and F. We're doing that matrix-matrix product over and over again in this loop. It's probably a bad idea. We can therefore say, well, X is equal to W if we do that outside of the loop, and then we replace that product down there. And so we only do the matrix-matrix product once, and it's completely equivalent. And the reason we can do that is neither W nor F change as we're running this loop. Those are fixed inputs and parameters. Okay. Yeah.
So you need a W for every length of the sentence, or the
No, crucially, W isn't. So F, so the dimensions here are, we've got F is going to be in n by the length of the sequence here. So it's going to have this, and W, we can say, is going to be in R of, let's just say it's n by n. So W doesn't depend on F, but when we multiply them together, the dimensions still work out. Yeah, good question. That's actually kind of the trick in a lot of these models, is you want to be able to deal with variable length things, and you can often multiply some axis of a matrix, have that fixed in every model. You wouldn't, if we say had both the number of rows and columns in F varying, then this wouldn't work. And that's one of the main reasons why we have a fixed number of dimensions. Yep. Okay. All right, so going back to our improvements. This is probably the biggest improvement in any MT paper I've ever read, was if you add attention to the sequence-to-sequence model, you got an improvement of 11 blue. Now, they're probably, if they had worked really hard to optimize the sequence-to-sequence model, it would have been closer to that, but this was, importantly, this was done in an academic lab, not at Google, where Suskever and all were doing their work. And so they just didn't have the GPU time to tune their sequence-to-sequence model, and they still got really, really good results. Yeah? Oh, yeah, blue. This is the standard machine translation evaluation metric that people report. It basically takes an expected translation and looks at the precision with which you generate n-grams in your translation. And it's been criticized for a whole bunch of reasons, but it's the standard evaluation metric. It ranges from 0 to 100. It's a percentage, and usually an improvement of 1 or 2 blue. Well, back in the old days, people were pretty excited about that, and so improvements like this were really unheard of.
So how many blues is the state of the art?
That's a. Well, blue is a really hard to interpret metric. You can't actually say what state of the art is on a particular task. You can really only use it to compare things. As a rough rule of thumb, I'd say if you have a single reference translation and you have system output that's getting in the range of 30 to 40, these are very readable sentences. But blue doesn't always correlate well with human judgments. In fact, there are ways to, you can get perfectly good translations that have very bad blue scores. It depends a lot on the language that you're translating. If you're translating from Chinese into English, you have a lot of optionality, and the chance of getting exactly the reference right, the n-grams in it right, is quite low, just because there's a lot of different ways to say things. And so even if you compare humans in terms of blue, they get much lower blue scores than, say, if you're translating Spanish to English, where translations are much more conventional and direct. So evaluation is a huge problem, and you've got to be careful of over-interpreting things. But if you're comparing 2 different models on the same test set, usually an improvement in blue is meaningful, and you will say, oh yeah, that's a better translation. And certainly if it's an improvement of 11 blue. Okay. All right, so here's a simple model variant that I bring up because it's used sometimes, and I also want to use it as an exercise to get you thinking about how we might analyze the computation in these models a little bit. So the model above is the one we just presented. And sometimes now this is referred to as an early binding model. So basically what you notice is we are computing our attention, weights, and context vector as a function of the previous hidden state in the RNN. A alternative to this is to not actually feed the context vector into the hidden state at time t, but instead use the information from the context only when deciding what word to generate. So basically, at time t, you're going to take the hidden state of an RNN over the output language, and you're going to combine that with the context vector, and then you're going to sample the translation. And so we're kind of, the arrow connects up at one level higher. So what do people think about this model? I'm not gonna flip the slide until somebody says something.
It's too late.
It's too late. I tend to think it's too late too. Why do you think it's too late?
I don't know. Like, context doesn't influence the hidden state.
Yeah, the context isn't influencing the hidden state, right? Or only very indirectly. Once you've sampled I, you're going to be in a slightly different hidden state, but that's a fairly indirect connection. So yeah, there's some notion maybe this is a little bit late. But sometimes we make modeling assumptions that maybe aren't ideal for computationally beneficial reasons. So can anyone think maybe at training time why maybe one versus the other might be, or why the second model might be a more computationally convenient model to work with?
The hidden state is more also recurrent.
Possibly, at least the matrices you need. So you could use the exact same size hidden states, but you would need, when you project the thing that updates the hidden state, those parameters would be different sizes. That's true. What else? So can you compute at training time? Do the hidden states depend on the attention values? They only use, given the word, they're independent of the attention states. Now at test time, they're all dependent on each other. But at training time, given those words, those output words, they're conditionally independent of those input states. And so those conditional independencies are useful. That means you can do anything that's independent, you can do in parallel in computation. So you can have two GPUs going, one doing your RNN for your input representation, one doing your RNN for your output representation, and then only later do you need to fill in how they come together at that higher level. So this model is quite a bit, could potentially be quite a bit cheaper to train, or at least there are some interesting opportunities for parallelization. So these are the kinds of tricks that, in the real world you have to worry about when you want to deploy these things. And I agree the model isn't very good. I think this neural MT is so new that there are a lot of ideas and they've only been compared pairwise in small areas. There isn't a systematic understanding. This model doesn't necessarily do worse, which is kind of interesting. But I'd say in general, the upper one does work better. Okay, so summary of this first part. So the first thing I'll also point out here is attention is really closely related to the pooling operations in ComNets and in other architectures. So for those of you who have this in your intro to machine learning class very often, when you want to reduce the output of a ComNet that's been applied to, say, an image, you do some kind of pooling operation and you pick out one representative vector to summarize, in some sense, an entire matrix or entire patch of an image. And that's exactly what attention is doing. It's just doing it dynamically. Another thing that I think when you're considering how you might improve models like this to note is The attention model here really only seems to care about content. And in fact, there's something a little bit strange about this model, which is when you're going to compute the attention weights of what to predict next, in some sense, if you knew exactly the word you were going to look for next, it seems like that would make it easiest to attend things. But if the model already had in its hidden state a perfect prediction of what it should be getting next, why does it need an attention mechanism at all? And so you might consider that the representation of the input that we use when we decide where to attend might actually need to be a little bit different from the representation of the content when it's retrieved and passed in to make the decision about what to translate next. So in general, we might think, if I'm translating from Japanese into English, where Japanese puts its verbs at the end of the sentence and English puts them, say, second, we'd probably want to query for things like, give me the next verb or something like that, not give me the next instance of the word apple. That's a little too precise. So you could imagine building in biases that let you compute attention using a different representation, or change the architecture that would let you compute attention using different representations. And some of this work is starting to be done, but again, I think there's interesting stuff here. Yeah?
Are those representations explicit labels when people are experimenting with that, or are they experimenting with like latent clusters?
Both. Well, not so much clusters, but latent representations that that have been trained so that they certainly contain the fact that this is a noun or this is a subject or something like that.
Okay,
That
so
sort of thing has been used.
semi-supervised.
Well, it's more multitask learning where you say, well, I want this representation to be good for translation, but also to be good for syntactic analysis, say. So we'll come back to this idea when I'm back in a few weeks, talking about how you can put linguistic information into neural networks. So another thing that we know about how words translate is they tend to have fairly characteristic patterns of the order with which words translate. So if you're translating between Spanish and French, the word orders are really pretty close. They're both basically dialectal variants of, vulgar Latin, and they're just kind of pronounced in very different ways. Apologies to any French or Spanish speakers who take exception to that. But even in other languages that are much more remotely related, there's a characteristic pattern of where you attend. And it seems like having to have the model learn from scratch without building in any prior bias towards what sorts of patterns are good or typical and which ones are not good is another weakness. So there's been a little bit of work that started to build in penalties that look at that attention grid that comes out at the end and penalize it if it's doing unusual things, and that can help a little bit. And so, and the other thing I'd say is getting back to this idea of interpretability, one of the nice things, if you actually train these models and look at the attention, you really do see some interesting stuff kind of popping out here. So here are a couple of sentences. These are translations from English into French. And you see, I like on the left here this very nice example. So French and English put the orders of nouns and verbs in a different way around. And so you see that it's learned to translate European economic area with this sort of inverted diagonal. But in general, things are moving along this diagonal here. Right. So, and the other thing you notice is this is fairly peaked. So, although we can have attention weights as long as they sum to 1. We don't really care where anything else about that attention weighting. But if these really at every time step, it's really kind of peaking its attention around a single position in the input sentence. Although there's some cases where things get smudged a little bit. So these things are interesting to look at. They help you understand how models go wrong. They also can give you inspiration for ideas for how you might make the models better. Okay, finally, a word about gradients before we move on to images. So I said at the beginning, gradients have a long way to travel. So imagine this is in our training data. We've got this sentence, "I'd like a beer." And let's imagine that beer, the model really didn't want to predict the word beer here. There was some problem with the parameters. So we're getting a big error in the cross entropy loss from that final position. So let's think about what attention is doing. So this weighting of these columns from the attention mask is just multiplying a scalar by each of those columns. So really, in some sense, what that matrix looks like once you've done the product is this thing here. And so for back propagating errors down to the representations of the words, what we're going to do is we're going to have gradients going all, following the arrows backwards as we do in back propagation, but the connections to this word where the attention is strongest, that gradient is going to be much stronger than the gradients onto other words in other positions. And so that means there's a much more direct connection at every time step. Basically, you don't, if the attention is good, and obviously the attention isn't always good because you're always learning this stuff jointly, but there's a fairly direct path. You don't have to traverse an entire LSTM history to go back and feed an error signal into the input representation the way you would in the Susskiver model. And so that's why I'd say this model does also help solve the forgetting problem that those old models have. Is that clear? Okay. So when I first saw this work presented, Kyung-Young Cho, who was involved in its development, asked this question. He said, does a translator read and memorize an input sentence, or even worse, an input document, and then generate the output? And that's kind of absurd. When you're translating something, you're kind of looking back and forth between the input and the output. You're relying on the fact that you can refer back to things. Compressing the entire input sentence into a fixed size vector basically says memorize the sentence. But common sense experience says translators refer back and forth to the input. And it's actually more than common sense. We have eye tracking studies of how translators work, and they actually do look back and forth all the time. And so, in general, this also kind of raises an interesting question. Should we be looking at humans in complex tasks like translation when we're trying to design our neural network models for tasks? This is an impossible philosophical question, but something you should think about. Okay, so that's all I'm going to say about translation. Are there questions before I go on to images? Okay. All right, so here's the translation we started with. There is another paper, we didn't actually talk about it last time, but it's exactly Susskiver, except instead of having an RNN reading a sentence up top, it's got a convolutional network that looks at an image, builds a fixed size vector representation, and then decodes. Absolutely no difference other than that. And it works pretty well. And see, it's a guy rowing, so that's my other Oxford theme thing. Then we can ask the question, can attention help solve the problem with, can we improve caption generation with attention? And there were actually a series of papers that all kind of came out at the same time, not a series, a batch of them, and they all said yes. And this is one of them from Xu and colleagues from 2 years ago. Very briefly, I want to point out that images, if you think about how convolutional networks work, and please, those of you who know more about these things than I do, if I say something really stupid, jump in and correct me because I don't work on these things at all. So basically what we've got here is we've got an image on this side, and we have little local receptive fields that are being moved all over the image and computing representations that are functions of these local fields. And if we stack these things together, what we have is an image, or we have a representation of the image that still has dimensional information, spatial information preserved at this high level. But it's now been stretched out, and there are features representing the contents of each of these parts of an image. So if you look at one of these little stacks of one of these sort of tube vectors in that final convolution, the output of that final convolution, that represents the feature content of some patch of the image. And Xu calls these things at this higher level layer of this convolutional network, he calls these attention vectors, annotation vectors A. And I'm going to switch back to calling them F because I want the notation to be consistent. So another way of thinking about this is we've got each one of these annotation vectors is looking at a particular field, a particular receptive field of an image. Now, it's a little confusing because the way these things work, you don't necessarily get a hard boundary on the edge of things, although I've drawn it that way, mainly because I don't know how to draw blurred things. But we have basically this vector A1 that summarizes the content of this blob up in, say, the upper left-hand corner of this image. And then we've got A2, and it overlaps a little bit with A1, and it represents the next patch, and we can do this all over. That's actually just what that last level convolution is. We're just going to reshape this tensor, which is going to be 3 or 4 dimensions, into this matrix. There's no other transformation. We're just lining up these vectors in this way. And now we've got a matrix F, and each column represents, you might say, a visual word almost. It's an embedding of part of the image. So you can think about the image as the sequence of vectors. So why don't we just run the same exact attention mechanism that we did in translation? We've got everything we need. We've got a matrix F, and we've got a decoder, and we've got some training data that says what the caption should be. So we can learn the same attention function. So we can do this. We can do deterministic soft attention. We compute AT. I'm not even going to review it. You can look at the beginning of things where C of T is just the weighted average of the columns. But in this paper, there's another innovation that I think is really interesting. And they call this stochastic hard attention. And the idea is that AT looks an awful lot like a probability distribution. Sums to 1. Each one corresponds to a particular event. And so instead of taking the weighted average, you can almost think of it as a expected value of the columns of F by sampling from that distribution, we're actually just going to sample from that distribution. We're going to pick out a patch of that image. And now we're going to say our CT is just whichever patch we've sampled. So first of all, do you understand what I mean, what the difference between these two models is? Right, so second time, every time I run this, I'm going to get a different answer, right? Or, well, there may be 20 different answers I can get, for one for each patch. So each time you run it, though, there's a flip of a coin. So why might we want to do this?
Because most of the image is irrelevant to the bridge.
Okay, but what if that was the case? Wouldn't we just learn to put 0 weight on those attention components, and they'd be zeroed out, and we would just be peaked around the right answer?
Isn't that what happens?
That's what happened in translation. Are images as easy as translation? What do you want to say?
If you sum up images, you're gonna get blurry thing, which doesn't look right.
Yeah, I think you're kind of getting blurry stuff. Whereas if you're sampling one thing, you've got your little patch, and that might be meaningful. And if we had enough data to backpropagate, maybe we learned filters that are capable of being averaged together in that way. But I think in general, in common, that's the way we train these things. We wouldn't expect that that would necessarily happen. So I think that's the really interesting thing is, yes, adding together, doing a weighted average of these columns and expecting that to give you something interpretable. Well, if you can learn that, you can learn to be additive. But you can't necessarily expect that if you just get vectors off the shelf. And crucially in this work, they didn't train their image component from scratch. They used a pre-trained model from state-of-the-art image recognition systems because there's a lot more training data that has images paired with this is a dog or this is a cat than there is caption stuff. A second point that I think is worth making here is, okay, there's a lot of variation in how you translate stuff, but in general, you have variation in maybe how you say the next word, but there's still a fairly narrow peaked distribution around the set of correct translations, and they all kind of look similar to each other. But if you give somebody an image, there are just a whole bunch of things you can attend to and you can translate. And so being able to decide what to look at next when you generate the caption seems sensible. I'm going to focus on, the picture of the banana in the corner, and then I'm going to focus on the picture of the car, and I'm going to ignore the fact that there's some guy selling pizza over here. There's basically that is very well captured by this model. Okay, so what are the challenges of doing learning in this model? Is this easy like the last one? Can we backpropagate through that squiggle? No, you can't backpropagate through the squiggle. If you had supervision for what the STs were, if somebody went through and said, okay, when I'm generating this word, I'm attending to this patch of image, then you could use cross entropy and you could train it just like, categorical distribution that gives you a probability of a particular ST. If you had a labeled thing that says I'm attending to patch 7 and the model didn't give you a high probability, you get a cross entropy out of that. So this is a latent variable. So we have to deal with learning with latent variables. And this is something this is at the bleeding edge of research these days in machine learning. It's sort of a perennial problem. It's been at the bleeding edge of research in machine learning for 50 years. In principle, the idea is easy. So we want to optimize the conditional log likelihood just like we always want to optimize. So log probability of W given X. But that extra sampling step that we've got in there, where we've got this variable S, now we've got a sequence of S's because at every time step for every word we're generating, we're attending somewhere else. We've got a joint model now of W and S. Now if we don't have examples of what those S's should be, the standard strategy is to marginalize them, so we sum them out. So there are a lot of S's here. If you had a lot of computers, maybe you could just write a big loop and loop over that, but how many S's are there if you have 20 image patches and you're generating a 5-word sentence? So at every time step, you pick one of 20 patches, and you do that 5 times in a row, and they all depend on each other. So it's 20 to the 5th. So it grows exponentially in the length of the sequence. So yeah, exponential sums are bad. And this third line, that's just the definition of our model. That is the independence assumption we made that is based on our design. So what Xu et al. Proposed to do is optimize, to minimize an upper bound on this quantity, which is justified using Jensen's inequality. It's a standard trick in a lot of latent variable problems. And you've still got this nasty sum here. And then they go one step further, and they replace that summation with an approximation, a Monte Carlo approximation of that sum. So you're just going to sample some possible trajectories, possible values of S, and then you're going to use this average, and n is up to you. It's a hyperparameter. In fact, they used n equals 1, and they still managed to learn some stuff. So basically, the algorithm is you sample n sequences of attention decisions from the model, and then the gradient is just going to be the probability, the gradient of the probability of the sequence scaled by the log probability of generating the target words using that sequence of attention decisions. So what we've got here is this component here on the end where we're conditioning on S. So we now, basically the model is going to give us some S's, and then we're going to check at the end, were those S's actually good decisions to have made? If so, yeah, let's support that. If not, maybe we'll ignore them. Or move away, actually. If they're really bad, we're gonna move, the gradient's going to push us away from those decisions. So they derive this in using a variational approximation. I actually found the description in the paper to be almost impenetrably opaque. They do point out this is equivalent to using the reinforce algorithm, which is an old policy gradient algorithm from 1992 that's used in reinforcement learning, and the reward that you get is the probability of the observed words under the model, the log likelihood there. And so this is a kind of, you could almost say this is a kind of reinforcement learning algorithm. Anyway, there are lots of ways to learn this. We don't really know how good this learner is because we don't really have anything better. Yeah?
So my understanding is that we have all these problems now because we have this sort of binary switch where it only allowed us one slice of the data. How about if we made it more structured, like Gaussian distribution? Is that not, would that allow us to kind of do the gradients, or?
You can never sample through, sampling is still discontinuous. So even if you had a continuous random variable, so if you, right now we're sampling, an exact position 1 or 2 or 3 or 4 or 5. And so that's a problem for gradients. We could imagine sampling from a continuous valued distribution, or a distribution that gives continuous values, a position, so you get sometimes position 4.73. You still wouldn't be able to backpropagate through the sampling step, but there are then some other ways of approximating this gradient that have lower variance than the reinforce algorithm has. And so there's a paper that actually came out, I think, at the same year at least, that used something called a reparameterization trick that does let you backpropagate through samples. You can in some cases backpropagate through samples if the parameter of the distribution, though, is a function of the variables you're trying to optimize. You can't backpropagate that, but you can rewrite samples from, say, a Gaussian distribution as a fixed mean times or plus some extra noise times the covariance, and that gives you then something that you can optimize, and it has lower variance. So yes, continuous values do help you. They're a little bit more optimizable, but they don't solve every problem, and you still end up resorting to sampling. But the samples become a little bit more efficient. Long answer to simple question. Okay. All right. So again, with this model, we can do cool things like look at what the model is attending to at every time step. So here we've got this picture in the upper left-hand corner, and then we've got this sequence of generations of a woman is throwing a frisbee in a park. We've got the probabilities of each of the words assigned by the model, and you can see this is the deterministic attention that model that they've got there. And so, as I said at the beginning, we don't have hard edges on these things, and they also added a smoothing, an extra smoothing thing for visualization for some reason, or for some reason I don't understand. So you can kind of see the model makes some sense. So when it's generating woman, it's looking both at the woman and the little girl, which maybe is a little strange. Throwing, it's looking at her, she's doing the throwing, so maybe this makes sense. Frisbee, models attending to the frisbee. But there are definitely some strange things here. I mean, you have to attend to something. So when it's generating the word A, it's looking at the little girl for some reason. And, that why would it do that? So this raises a bunch of questions, it comes up with some ideas for how you might improve this model in various ways. Yeah.
People ever gate attention, like turn attention on and off?
What do you mean?
Like put a gate on whether or not to use attention at all? Because like there's sometimes here when it seems like attention is just more distracting than helpful.
There's been some work on giving it kind of extra image things to attend to that are hopefully there to consume some of that, and I guess you could kind of understand that. If you had, I guess I'm not aware of work really that decides whether to, or has a deterministic decision about whether to gate things or not. Phil, are you?
Well, in language, yes, there's the sense of quick stuff.
Oh, right. Okay, sure. Yes, there is a. We just wrote a paper about this. I guess I thought about that in a slightly different way. So one of the challenges with gating like this, if you actually make a decision, I'm going to use attention or I'm not going to use attention, you have another stochastic variable, and then you're back to this latent variable problem. You can have a deterministic sort of how much do I trust attention, and that could range between 0 and 1, and that could be deterministic gating. That was actually what I was asking about, if anybody had done that. Are you aware of that? Not deterministic. Okay, this is a good project for somebody to try. It's an intuitively good idea. Another thing right, this is a big problem. We shouldn't maybe always be looking somewhere. We should think about where we should be attending. Maybe we should be attending inside of our heads or to past words. Maybe we should have multimodal attention where we can think about the fact that I'm at this position in the sentence, and so I'm saying, well, I always say the word of at this position, so I'd be attending to the word. And then sometimes we should learn to go and attend into the image. You could do something like that. Lots and lots of things to try. Another thing you can do with these models is look at when the model produces something that you don't expect. You can look at what the model was thinking. So I love both of these examples. The first one says a woman is holding a clock in her hand, and that shirt really, you can see, okay, yeah, that does look kind of like a clock. And the model you can sort of imagine these models as having really bad vision and sort of saying, well, I think this is what I see, and I'm just guessing. And so that's what's going on there. And the second picture, I actually couldn't really see what those things were either. And they are two giraffes, and it thinks it looks kind of like a white bird, and you can say, oh yeah, it's sort of tall, long neck thing. Those are usually birds. And so, in both of these cases, you do see that the model is at least looking in the right place, and here it's just misinterpreted things. And so the answer to that is probably, well, we either make the ConvNet more powerful, or we do better pre-training of it with more images so it learns. That's not a clock, that's a sweatshirt. On the other hand, one of the other things you do see in this is often the network will say a girl is playing Frisbee, and it won't even be looking at the Frisbee when it generates the word Frisbee. And that's a much more concerning problem. It probably just says, well, in the data set they trained on, there were a lot of pictures of people playing Frisbee, so whenever you played something, it was probably Frisbee. And then you can realize, that suggests other problems. So looking at attention is a fun thing to do, and it can be useful as well. Okay, so attention and captioning. It helps, again, maybe not as much as it did with machine translation. Another problem, though, using blue to evaluate caption generation is a lot harder. So the human upper bound on blue performance is much greater than it is. Actually, the blue scores are fairly close to what a human would give you, and they're far away from 100 on this task. Just there are too many ways to talk about a particular image. So so again, I wouldn't look at maybe try and compare that to the 11 we got on translation. And it does seem that hard attention helped more. One thing I will also mention was they reported 2 metrics in this paper. So blue is just one way of evaluating translation. They also reported one called Meteor. Meteor knows about synonymy and things like that. And actually, hard attention tended not to do better on Meteor. They worked about the same, or the deterministic attention even worked a little bit better. So depending on how you look at the results, the difference between the two wasn't huge. And obviously implementing hard attention is a bit more, a bit riskier. But by and large, attention is still is a great idea, both for translation and captioning. Okay, so it's 12:30, but I'm getting finished here, so you guys can finish asking questions. I'd summarize this lecture today as saying, well, basically attention was one of the things that's really made deep learning for conditional language generation an incredibly powerful technique. So we get better improvement over, big improvements over vector-based encodings. We also get good improvements, or we do very well with much smaller training data. So in principle, LSTM should be able to learn everything that they need to know given enough capacity. But we don't have enough data, and they're very hard to optimize. The second gain that we see here is model interpretability. Once we start knowing what the model's thinking, we can start trying to correct it and make it think a little bit more intelligently. We've got better gradient flow, which is a nice thing to have in terms. That's one of the reasons why we get good learnability. But also, when you're designing networks, you should be worried: what's the longest distance an error has to travel if I want to learn something successfully. And another component of these or another success of these models is we have better capacity of representation of the inputs. And one way you see that is when you compare these models that use attention to models that put everything in a vector. You'll see, if you plot the performance, say blue versus sentence length, you'll see curves like this for sequence to sequence with vectors in the middle. And you'll see curves that look much more like this for for models that put a matrix in the middle with attention. And so basically, short sentences get learned. Both models do really well at translating them. But then the longer sentences, that matrix, that extra capacity really, really helps. And so, in fact, you probably, the other thing that's interesting is short sentences, they both translate just as well in either model. So it really is an issue of memory, you might say. Okay, that's everything. So are there any questions about today's lecture? Yeah.
Coming back to the earlier point of the sampling, what I meant is actually more similar to what you proposed earlier, where we're adding up the vector. Is there a way that we can do a normal distribution and then just everything activates to some extent and you just add them up together? Would that then be soft attention that you can still have gradient descending?
Is the idea then that you would be you'd be taking the expectation under that continuous distribution?
Right. So basically, you would still have kind of adding the convolutions together, but by the nature of by kind of restricting to relatively peaky Gaussians, you add very close convolutions.
Yes, you could do that. So this is an interesting idea. Phil and I once actually talked about doing something like this for not just for images, but for translation. The idea is your attention, rather than being a a single a distribution in some sense over positions. It's a value, and we want to basically have a regression on that value. And then maybe in addition to just predicting the value, we also predict something like a variance. And then so we don't actually have to sample from that value, but by the nature of that representation, we're predicting a single position. And now we have to convert that position into something that gives us a single vector. And that needs to be differentiable and continuous. So we can say, well, this is just a mean and variance of a scalar or a univariate Gaussian in the case of a sentence, or maybe a bivariate Gaussian in the case of an image, picking a position out, and then you compute the expected value under that distribution. And that's a deterministic function, and you can differentiate with respect to that expected value. So yes, I think that's a great idea. I don't know if anybody has done that before, but yeah, cool.
Is the research on going beyond this window of a single sentence, this token?
Good question. Yeah, so if you're translating, very often how you translate a word depends on the context it's being used in. And say you're translating from Finnish into English, and you see the pronoun hen, which means either he or she. And I think a lot of languages, Chinese maybe has that too. You would very much like to look at the previous sentence to figure out, am I talking about a man or a woman when I'm using this pronoun? And there has been a lot of attempts to work on this, and obviously you can imagine architectures that let you condition on surrounding context. I think this is one of these problems where we don't actually know if we're doing very well. So certainly conditioning on surrounding context doesn't improve models, at least the models we've come up with so far. We don't see big improvements for doing this. But there's a reason to think that we aren't actually very good at knowing whether we're doing well or not. The influence that surrounding context has, it doesn't change the way things translate profoundly. It changes a few words here. It changes maybe the tense of verbs in Chinese. It changes genders of pronouns in languages where you've got lots of complex gender information. It matters, but the way we evaluate translation is we don't actually know, or I don't think the test sets that we have, they're mostly on domains like news, and so we don't actually think that those things play a huge role in them. If we were translating things like conversations, where there's much more information present in the foreground and we sort of complete each other's sentences, there my guess is we would see improvements, but we just don't have that data. And so in order to really work on this, we need to create better test sets to know whether we've actually succeeded in learning something, I think. That's one hypothesis for why we're not seeing improvements. The other is our models just aren't ready. So intuitively, yes, I think this is great. There has been a lot of work. So far, it's been kind of a failure.
A failure?
Yeah, I mean, in the sense that it doesn't improve over treating sentences independently. But lots of people are interested in this question. Yeah.
So how good are like the current models at sort of nested context? So if like two people are talking about maybe 3 or 4 other people, then I can say he, she, they, and how good are models at sort of keeping these dependencies and inferring who he is and who she is?
Well, our models we don't really know what they're thinking. And we're only starting to look at very surfacey stuff, like how much are the models figuring out, say, about the syntactic structure of the sentences, because we don't teach them anything about this. So, and we just see vectors at every time step. So knowing, are they keeping track of entities internally is hard. We haven't even, for things like that, done very much we haven't done very much at looking at their behavior on a specific phenomena like that. Are they getting confused with co-ref? One thing they don't do, which you'll see in translation, is if I'm talking about somebody like, if I'm talking about Barack Obama, I might say he, or I might say the former president. And in translation, I could directly translate that, but I might also just come up with a new way of referring to the former president because maybe it flows a little bit more naturally in translation. So that's something a human translator would do, and it's not something that, our models tend to be very direct. And in fact, I'd say we have more basic problems right now, which is if you look at the way neural MT systems work, they will very often produce output that they'll either drop part of the sentence or they will say something that sounds good in English in the target language, but actually isn't what's said in the source sentence. So this is kind of new in all of the models we used to work with. They would very strictly adhere to the input, and they would always be explaining the input sentence. And now they kind of get a little delusional from time to time, and they just start talking about random stuff. And that's an issue with conditional models like this in general. It's a kind of explaining away effect that happens. So I think this is one of the big questions in terms of how are they really processing language in a way that we are, where they're tracking entities and things like that. I think we are still a little way away from being able to really even know how to ask that question, let alone answer it.